All right. First thing that you need to understand is you're asked to understand about the structure of metals. And I gave you 2 PowerPoints to look at about that, and also it is in your textbook. Essentially, what you're asked to understand is the way that electrons are shared in a metal and about the lattice structure of it. So what you need to understand is that metals are actually crystals in form. They have very irregular structures. Okay?
Very irregular?
Very regular. A crystal is simply a set of atoms joined up in a regular pattern, so you end up with a lovely thing like a diamond or, you know, sapphire or tourmaline or one of those objects.
What's the space between the lattice?
Well, don't think it's not quite that way. So, if you, and this is very poorly drawn, I'll do it relatively quickly. You can imagine that if you have a cubic crystal, maybe galena or sphalerite or something like that, you've got a series of atoms which have a very large centre. Now, in my poor drawing technique, I'll try and do it like this. So imagine there's some the 4 back ones. They're back into the board. And they are linked by, they're linked, right? No, they're not ionic bonds. It's metallic bonding. Because you would have learned, okay, so imagine that's a cube, right? Which you can kind of get a picture of. Okay. Now, when you're dealing in chemistry, you're typically taught about covalent bonding and ionic bonding. Covalent bonding is where 2 atoms share electrons to satisfy their need for energy balance in the outer shell. You can have covalent, which is where, sorry, not covalent, ionic, which is a charge. Another atom picks up that charge, they become oppositely charged, they're attracted. In metallic bonding, it is slightly different. The reason is, this is what you should have found, is that doing. In the case of the amount of energy that these electrons, our electrons possess, is actually enough for them to be released from the atom. So they've got enough energy to be released from the atom, and their paths are close, which means that they share. Exactly, and that's why it's easy for them to flow. So essentially, the electrons are being shared in the lattice, all through the lattice, and so you have this whole selection of electrons which are not bound to any given atom at any given time. They just move through fairly randomly, and some will be going one direction, some the other, and all over the place. So you don't get net electrical flow, but you do get them just floating around. And that's often called the sea of electrons. flow through it, do you?
Electricity.
Now, what's the difference between a conductor and an insulator?
One really conducts electricity.
One readily allows current to flow through it, and one doesn't.
has easy access to it.
Essentially, yeah. For example, air is basically an insulator, right? But is it a perfect insulator? No. And I know it's a relatively good insulator because if I walk past a power point that's on, I'm not scared by that. It's not going to flow through and connect with me, is it?
The voltage is at the high.
However, if you've got a high enough voltage, you go up to a 330 kilovolt transmission line, and you climb up and put your finger out, you may well regret it because it will go through air and it will kill you.
But what is it about the putting more charge in those electrons that will make it arc?
No, you're not thinking that. Careful of your terminology there. We don't talk about charge as such. You know, you have to talk about your voltage and whatnot. Well, it's like this. If I want to get a ball to hit you, if I just dribble out of my hand, it hasn't got enough energy to reach it.
Yeah.
But if I really ping it, it's going to get you because I've given enough energy to get there. So
It is a 3,000 kilovolt, and then probably a big potential difference.
there is a big, yeah, there's 330 kilovolt potential
All
difference.
make it arc.
If you get close enough so that if the distance is small enough, the voltage will be such that it will pass through the air and get to you, and you'll learn that later on in the next topic, yeah.
What about birds flying in those high voltage power lines? They get just
In the air, there's no grounding, so there's no potential,
So that's why they can sit on a power line.
as long as they're on one line. Occasionally outside houses you see bats who've decided foolishly to cling onto two lines,
Dumb bats.
and if they don't cling onto one with the same potential across them, you know, same voltage, they'll end up being a
I don't
potential.
understand if you climb that tower and
You're connected through, well, most of those towers are metal.
yeah,
That means you're earthed, which means you're a ground state, you're zero. If a bird sat on a tower close enough to the wires, on the bad day it would get zapped.
So if we do that, we're shorting the whole wire. So what? Let's just jump straight us and go to the other end.
right. So but you could also do it in a way of like if you were climbing up the tower and then you leapt and grabbed onto one line.
If you could get close enough to leap 330 kilovolts, you may get 1.5 to 2 meters arcing.
Is the same?
No, but like if you could leap that distance.
Yeah, but if you had to climb up,
Yeah.
you'd have to be able to jump onto the wire from a distance of over 2 meters to
Yeah.
guarantee you to get zapped. Yes,
You would just grab onto it and you'd be fine.
yes.
As long as you grab it.
In fact, you can see line workers actually holding onto these things and working on them.
What are they onto both of them?
No, one at a time. They wouldn't go both.
They have to like, turn off the actual power if they're working on it. If like they're falling.
No, they use Faraday suits.
But what about when they're on the ground?
Yeah, well, there are protocols, and yes, they do switch them off in that line if they're on the ground working at them and things like that. But anyway, that's the metal lattice. Insulators, the electrons are tightly bound; they can't be influenced to move, so you're not going to get current through it, right? Semiconductors are this small class of elements, if the so-called semiconductors have a whole opportunity for people to create technology. G'day, that's right.
Could I see Josh at lunchtime?
Yeah, I think so, if he can hear you.
Stuff to do. That was really
Josh, when they get back to you already?
second last. I've got you first last.
No worries.
Okay. The other thing you can do, and this is the stuff you were supposed to be learning, guys, and I had to work through this relatively quickly. The other thing you can do is you can what's called doping the semiconductor.
What's that do?
Put impurities in it which make it much more conductive. And it's much more efficient.
Can you
Now,
a superconductor?
no. Impurities in a superconductor are a very bad idea. Why? Because any impurity in a lattice will stop the flow of electrons, so it increases the chance of resistances.
Then how does a semiconductor work?
Right, semiconductor, don't forget, relies upon the fact you want to remove an electron or two to create holes, or if you can shove a couple of electrons in, you can then create a negative region which makes it go on. Now, what you can have, originally they used to use germanium as the semiconductor in making things, and now it's silicon. Germanium was cheaper to actually purify when they started with it, but the biggest issue with it was that it's not very abundant. It's hard to get hold of. That's right. It was only once they worked out a new technique for getting silica pure. The thing about silica, make it extremely pure, but the beauty about silicon is that we make our glass out of silicon. It's just sand. So you can dig up sand, whereas germanium, you have to actually go and find these rich ores of germanium and dig them up, and they're very rare.
Silicon acts superconductor if you cool it to the right level.
Everything's superconducts if you cool them up, yeah.
So, you know, when we do superconductors, this topic, do we get hold of the magnet over because they repel the magnetic field?
I want to, but I have trying to get hold of the liquid
liquid
nitrogen.
We're HSC physics students. Shouldn't we be able to do that if you can get liquid nitrogen fission?
Yeah, yeah.
So if you freeze something, you get something cold, it becomes superconductor.
Yes, but that's another topic. Right, so what you do,
There's so many jokes that you make with that.
So what was it about the lattice superconductors?
no, it comes to the next topic. Let's not get ahead of ourselves. Right, P-type. There's a periodic table of the elements at the back. Right, if you have a group 4 element, germanium and silicon, how many electrons do they have in the outer shell?
6, 8, no, 1, 8, 8,
4. If you have a group 3 element, how many electrons will it have?
We don't do chemistry, sir. We're physics, not chemistry.
Group 3.
3.
So if you take, now this is what doping is. They put 1 additional atom per million.
1 per million.
Its strength is 1 part per million, and that's a very strongly doped thing. And you might put a group 3 element in it.
Is that just like putting 1 gram to 1,000 grams?
1 part per million. It'd be 1 gram per ton.
Wow.
Just out of interest, when I was mining gold, or in a company mining gold, we used to work for gold at that purity, at that level. It was economic back then that you could actually mine gold you couldn't see. If you could extract 5 grams per ton, that was good enough back then. 5 grams per ton was good enough in the ore to make it economic.
You'd
Rock.
You'd make more off the rock that's not gold in that extract than you would off the gold.
No, that's back, but now it's getting back towards those levels actually.
You know,
Anyway.
in all of human mining history, the most gold that they've got doesn't even fill an Olympic swimming. All the gold. That's a lot of gold.
So,
Doesn't.
I can't remember my group 3 elements. boron with their electrons sharing with it. But boron only has 3 electrons in the outer shell, which means there's a hole there, a positive hole. So you know how we had to eject an electron before to make it start the chain reaction of the conduction? Now there's actually a space for an electron to go. That's a p-type semiconductor. In the n-type semiconductor, you can imagine you take group 5 element, you put it in there, it has an extra electron. So when you look at it with the silicon, there's the central silicon. It has its 4 electrons around the outside. You have the associated silicons. And then you have the group 5 element, which I call E because I can't remember off the top of my head what it is. It's going to have an electron there, electron up there with a silicon, electron with a silicon, electron with a silicon, and electron. Has an extra, no, oxygen's not 5, don't think. But it has an extra electron in there. That means there's a couple of extra negative charges in there, and it will then push other electrons out of orbit and make the conduction occur, right? Now, the thing about this is that, as I've stated earlier in this lecture of stuff you should have already done, you will recognise that the reason we're looking at this is silicon chips, diodes, and so forth are really, really important parts of our current technologies, and particularly with making computers. So this stuff that you guys are using at the moment are reliant upon this technology for a couple of reasons. It allows us to control and manipulate current flow. Now here is what they used to have before we made silicon chips. Does exactly the same job. These are thermionic devices. And what I have here is a triode and no, it's actually a CRT deflection screen. The original ENIAC computer was made of these. And not only was it made of these,
There's an electron gun which fires it, and then an accelerator. There's 2 pairs of charge plates which then projected onto a screen, and in a TV there's 3 of them for the red, green, and blue ones, but then they individually project onto a pixel.
now what I'm hoping here is you'll be able to see how it works. The original computers are made of these. The original TVs, which I first used to watch, had piles of these in them.
Coming up next, ABC one.
Yeah, I don't want that one on. I want the other one.
Sir, you're right. That's 4 Olympic circles worth of gold. That's still not much.
That's just bent the other
That's like barely.
There we go. Yeah, we'll bend the other one. So what you got here, quite simply, you've got a glass tube that's evacuated. You've got a circuit that runs around the back of it. Right? Well, you actually have an emitter and a collector.
What's happening there? I see. Oh, I can see.
What I'm doing.
So those thermionic devices firing electrons.
So the reason these things create electrons, they're delicate. If you touch them, you put grease on them, and they don't work so well. So what do you notice about those wires? What are they doing?
They are heating.
They're heating. Thermionic devices, thermo, heat,
Yeah.
right? And
They allow better flow of electrons, which means more can be released.
yes, exactly. And in fact, with a triode, this is slightly different, but in a triode, you have an inside, you have a heating element, you'll have a collector around the outside. And if you put a third, when you flow current through the third arm of the transistor, acts as an amplifier. It actually makes the larger current. And as you can see, what I can do is by increasing and decreasing the current flow.
That's the way to go with that red. Just going. The what? The red. Like red. Red. The red. Orange.
So see what happens with the red there? What's happening there?
Oh, he's talking about the label there. I'm calling bullshit. How can you not see that's orange?
So what's happening is as I increase my input voltage on the thermionic part of this thing, right, it's changing the amount of the cathode rays being released.
Oh, yeah.
That's orange.
Sort of got here.
Waiting for the old
I understand what is happening here, sir.
Hmm?
I understand what's happening.
Oh, I want that one on. That's what I want.
All I'm seeing is different lights. That's what, like, what's this demonstrating?
Well, what it's showing is what a valve and a thermionic device is. All right. Now you're supposed to learn how to work a thermionic device.
Can I adjust it?
Yeah,
That'll
you
make
can.
a really cool metronome.
Oh, sweet. Where's the other one that you can adjust? Oh, sweet. So that's the magnetic.
So you got electronic deflect device. But look underneath. What's creating the electron beam there? Can you see what's creating the electron beam?
Yeah, the thermionic.
The heated element is throwing electrons off. It's thermionic. Now these things work perfectly well. I could build a modern computer with these.
Let's turn on the.
But
You need a room.
no, I wouldn't need a room.
Wait, what? That being heated is emitting electrons.
Yes,
Why?
because you're
That's
putting
the
energy in.
That's the cathode, and because they're being heating it, the electrons move more, and therefore they can be
So
fired
with
more.
the first one, because like you went past a certain voltage and then it actually.
Oh, so then we have
created
devices
a line.
semiconductors.
Right.
So is that what you mean? The thermionic device is semiconductors?
No. What you can do is they learn how to make
No, can I flick on?
transistors and diodes and things using these devices. But now we learn how to go to solid state, which is using semiconductors.
So I don't understand what's going on here.
So
All right.
like with the first
You're
one.
heating stuff, so that beam is being heated up, and I don't know what it's doing.
When you heat it up,
Yeah?
it's simply releasing a lot of electrons
Why?
because you're putting enough energy in that they absorbed in the atom, and the atom has enough energy in it that throws. No, it's not photo because that would mean light.
Oh,
This is done by heat.
infrared effect.
Look at all the electrons coming off that. Oh, I can see every one.
Because like once it gets past a certain point, it would start actually transferring the electrons.
So in Thomson's charge to mass ratio experiment, when
So you don't have heat measure on electric effect.
No, forget photoelectric effect. Guys, sit down. Right, let me explain before you run away. Because we're going to run out of time, we need to move on. You can, right, essentially a transistor in a current computer is a single switch which switches on and off. So you put a current through it, try to put a current through it, and you have a third arm. And if you switch on that current, it will allow current to flow. If you switch it off, it won't allow current to flow. And so you've got something which will operate as a switch
The semiconductor, because they won't let
in the semiconductor. But you can build exactly the same thing with these things. Now the thing about these things is, in a space that big, I can make a million, or actually a billion transistors using silicon. Whereas I need one of those for one transistor. So to make a modern computer, I need to have a billion of these sitting in a framework, consuming energy to work. Now I could do it, but you're going to have a couple of problems.
size.
You're going to have size. They're very delicate. If you knock it, they're glass, they break. They consume huge amounts of power and they produce a lot of heat. So if you put them too close together, they melt each other.
So if all TVs use that thermionic devices,
Yep.
how did plasma TVs work?